Welcome to our channel. In this video we understand array data types in Schneider PLC EcoStruxure Control Expert. First, open your EcoStruxure Control Expert and create a new project. Select PLC and its slot, and press OK. Now go to Project Properties and change Password, and press Apply and OK. Arrays in Schneider PLC EcoStruxure Control Expert let you store multiple values under one name, making programs cleaner and easier to manage. In this guide, you'll learn how to declare arrays in structured text, access individual elements, use for loops to manipulate array data, and work with multidimensional arrays. Practical examples, common mistakes, and best practices are included to help both beginners and engineers understand arrays easily. An array data type in Schneider PLC EcoStruxure Control Expert is a data item that contains a set of data elements of the same type. Arrays allow you to group multiple related values under a single name, making programming cleaner and easier to manage. Array_real is single dimension array data type. A single dimension array. A simple list of elements that can be accessed with a single index. Array_int 0 to 10. 0 to 10 is a two-dimensional array. It behaves like an 11 by 11 grid of numbers. The first index is the row, the second is the column. Each cell can hold a 32-bit integer. For example, array_int 3, 5 means the value stored at row 3, column 5. Array_bool 0 to 10, 0 to 10. 0 to 10 is a three-dimensional Boolean array. Think of it as an 11 by 11 grid repeated through 11 layers, like pages in a book. The first index is the row, the second is the column, the third is the layer. Each position stores either true or false. For example, array_bool 3, 5. 2 means row 3, column 5, on layer 2. First, a single dimension array. Array_real 0 is assigned the value 12.234. Then array_real 1 is set equal to array_real 0 multiplied by 11. This means the second element stores a value based on the first. Next, a two-dimensional array. Array_int 0, 0 is given the number 1121. Array_int 1, 0 is given 1112. We can also write row and column together. For example, array_int 2, 0 equals array_int 0, 0 multiplied by array_int 1, 0. Think of this array as a grid with rows and columns, where the first index is the row and the second is the column. Finally, a three-dimensional Boolean array. Array_bool 0, 0, 0 is set to true. Array_bool 1, 0, 1 is also set to true. A three-dimensional array is like a cube made of rows, columns, and layers. Each cell in that cube can hold either true or false. This shows how the same concept extends from one dimension to 2 and then to 3 by adding more index positions. A three-dimensional array is like a cube of storage boxes. Each position is identified by three coordinates: the row, the column, and the layer. In our code, we declared array_bool 0, 10, 0, 10, 0, 10. That means there are 11 rows, 11 columns, and 11 layers stacked one behind the other, giving a total of 1,331 cells. When we write array_bool 0, 0, 0 equals true, we are turning on the box at row 0, column 0, layer 0. Think of it as the front top left corner of the cube. The statement array_bool 1, 0, 1 equals true sets the value at row 1, column 0, layer 1. That is like moving one step down, staying in the first column, and going to the next layer inside the cube. Every cell in this cube can only hold true or false, which is perfect for flags, on-off states, or logic maps. By changing any of the 3 index numbers, you move along a different direction in the cube. The first index moves up and down rows. The second index moves across columns. The third index moves through layers. This mental picture of a stack of grids, or a Rubik's Cube of booleans, makes it easier to see how three-dimensional arrays organize large sets of on-off data. Now we see how to use an array in ladder language. We start by simply adding a multiplication instruction to multiply the contents of 2 array elements. In the first rung, the MUL block takes its first input from array_real0 and its second input from array_real1. The block multiplies these 2 real numbers and sends the result to array_real2. If the first cell holds 12.2 and the second holds 11, the block writes 134.2 into the third cell. Because the PLC scans continuously, this result is recalculated on every pass, so if either input changes, the output updates instantly, almost like an Excel formula that never stops refreshing. On the next rung, we repeat the idea with a 2-dimensional integer array. Here the MUL block reads row 0, column 1 as its first input, and row 0, column 2 as its second. The product is stored in row 0, column 3. For example, if row 0 column 1 contains 50 and row 0 column 2 contains 4, the block writes 200 into row 0 column 3. Think of the 2-dimensional array as a table where each cell can directly feed logic blocks without extra wiring. During simulation, you can watch these cells update in real time. The enable line remains true. The function block recalculates on every scan, and the destination element in the array always shows the live product of the 2 source elements. This makes it easy to test. Simply type new values into the source cells and observe the change ripple through immediately. By combining arrays with simple math instructions, ladder logic becomes far more flexible. Instead of hardwiring every tag, you can treat the array like a dynamic spreadsheet inside the PLC. This is especially powerful when scaling to larger projects, looping through rows and columns, performing bulk calculations, or logging results for later analysis. Even with just one MUL block, the principle is clear. Arrays turn repetitive math into organized, reusable logic.